All right, hey guys, this is the beginning of Unit 9, which is on factoring. So we're going to look at basically a lot of different things with factoring, but eventually our goal is to be factoring different polynomials, whether they're trinomials, binomials, or whatever. We need to start though by talking about prime factorization, kind of how we break down the number into prime factors, and then use that to talk about the greatest common factor of monomials. And that's going to lead us into our third topic there, factoring polynomials using the greatest common factor. And we'll get into the rest later this unit. So let's start with prime factorization. So our question for now is, how do I write any number using prime factors? In other words, breaking down something into numbers that basically multiply up to that product, that value. So when we say product, we're referring to the result, right? The result of one or more multiplications. The factors then are those numbers that we use to multiply together to get that product. As an example, if 3 times 5 equals 15, 3 and 5 are the factors. 15 is what we consider the product. Okay, so when I use that terminology, factors, I'm talking about the parts or the things that multiply to get the product. So for prime factorization, okay, let's review what a prime number is. A prime number is a number whose only number factors are 1 and itself. For example, here are the first, the first 10 prime numbers. All of these numbers can only be divisible by the number 1 and itself. So 13 is only 1 times 13. There's no other factor pairs that will multiply up to 13 using whole numbers. 11 is just 1 times 11. 7 is just 1 times 7. There's no other numbers you can divide out of these except for 1 and itself. That makes it a prime number. So prime factorization is writing any of the other numbers, those non-prime numbers, using prime number factors. For example, the number 4, you'll notice, is not in my list up here of perfect or prime numbers. So 2, 3, 5, 7, 11, and so on. So 4 is not a prime number because it can be rewritten as 2 times 2. It's a product of prime numbers. 2 is a prime number. 2 times 2 represents the same thing as 4. That's prime factorization. So to give the prime factorization of 15, one way we can do that is using what we call a factor tree. Just draw a couple branches and think about, well, what two numbers multiply up to 15 other than 1 times 15? We don't ever want to split it up that way because it doesn't really split it up if it keeps it as 15. So I know that 3 times 5 is 15. So I put 3 under one branch, 5 under the other, and then I check to see it. Can I further make branches down my factor tree? Can I split up the 3 any further? No, because it's a prime number. And I can't do 5 either because that's a prime number. So 15 is the result of 3 times 5. The prime factorization of 15 is 3 times 5. For 48, there's lots of different ways you can multiply two numbers together to get 48. I'm just going to start with, a multiplication fact I remember from the multiplication table. 6 times 8 is 48. But then I know that 6 can be broken up even further, so it's not a prime number. I can write it as 2 times 3. And I know that 2 is a prime number and 3 is a prime number. So then I focus on the 8. I go, well, what multiplies up to 8? 2 times 4 is 8. And 2 is prime. But 4 is not prime because you can break that down as 2 times 2. Prime numbers again. So my prime factorization of 48 contains 5 numbers. And whenever you write the prime factorization of a number, we rearrange those prime numbers from least to greatest. So I had a 2, another 2, another 2. So 1, 2, 3, another 2, and then finally a 3. So 48 is the exact same value as 2 times 2 times 2 times 3. It's just that we have prime factors when we write it as 2 times 2 times 2 times 2 times 3. I think I said that right. Now, when we want to give prime factorization of a monomial, remember we discussed monomials last unit? It's a polynomial where there's only one term, so there's no pluses or minuses in it. We can do the same thing. We break it down first by number, So we're going to focus on the prime factorization of 30. So 30 I know is 3 times 10, and 3 is a prime number. But 10 can be broken down as 2 times 5, which are both prime numbers. So 30 is actually 2 times 3 times 5. Notice when I find a prime number, I circle it. That's because when I rearrange them, I know exactly which numbers to write down. And don't accidentally write down the 10, for example. So 2 times 3 times 5 is 30. Now for these variable parts, we just write it in expanded form. So x to the third power would be like x times x times x. And then the y at the end is just another y. So 2 times 3 times 5 times x times x times x times y. So our fourth example, we want to start by trying to break down the 48 into prime factors. And actually, didn't we just do this on 48? We did. It was, let's see, 2 times 2 times 2 times 2 times 3. So I had 4 2's and a 3. So I'm actually going to save some time. I already did the work on the previous problem. So I know it's going to be 2 times 2 times 2 times 2 times 3. So 4 2's and a 3. And all I have to add at the end is the m's and the n's. M squared means I have m twice, and n squared just means I have n twice. So there's the prime factorization of 48 m squared n squared. Now there may be a time where it asks for the prime factorization written in exponential form. So exponential form is when you use exponents anytime you have the same prime factor appearing more than once. Okay, so exponential form of 48 m squared n squared would be 2 to the fourth power times the 3 times m, which appeared twice, times n, which appeared twice. So that's just another way that you can write the prime factorization. This first way is what we call standard form of the prime factorization, which is just listing all of the prime factors expanded out. Exponential form is when you use exponents to show what those factors are.